Alright, cherubs, right now we're looking at a wall within the Alhambra in southern Spain. As many of you may know, Islamic Moors once occupied much of modern Spain, and the Islamic faith prohibits pictorial depictions of God or Muhammad. Consequently, the walls of their important structures were not covered in mosaics of important religious or political figures like those in the Byzantine Empire, nor were they covered in frescoes like those in Italy, but designs like these. The belief here is that accurate depictions of the physical world can be misleading. An image representing God could lead to the worship of the image rather than God himself. If one wants to depict divine beauty, therefore, one should not seek a literal representation of the divine, but some kind of abstract intellectual beauty. A beauty that exists in one's mind, a metaphysical beauty, is greater than the beauty of the body. The magnificence of symmetry and pattern forces our intellect to engage with the world of the divine, and so the Moors use these symmetries to show the brilliance of the mind of God, rather than the physical beauty of his body. So let's look more closely at how symmetry works. We all have an intuitive feel for what things are symmetrical and what things aren't, and some things feel symmetrical even though they don't have a line of symmetry. Mathematicians formalize our intuition by focusing on transformations of an image, instead of on the image itself. For any object, picture, or structure, mathematicians say that it has a symmetry if there is an action on the structure that leaves the object unchanged. For instance, if we rotate the wall 90 degrees, centered at this dot, our picture of the wall would look the same. This wall has 90-degree rotational symmetry. If we were to rotate the wall 45 degrees, our picture of the wall would look different. This wall does not have 45-degree rotational symmetry. Part of what makes the Alhambra's walls so beautiful is that they have lots of different symmetries. You could reflect about this line, rotate by 180 degrees, and many more. A mathematical question to ask would be, how many different symmetries does this wall have? Can we find or classify all the symmetries of an object? The walls of the Alhambra are a little daunting, so let's try something simple first, a triangle. What can we do to this equilateral triangle without changing its appearance? We can rotate it one turn counterclockwise, 120 degrees. We can rotate it twice counterclockwise, 240 degrees. We can reflect it along the line through point A. And we can reflect it across the lines through B and C as well. Now there's one other you might not think of. We can just leave it be and not do anything to it. Think of this as picking it up and putting it back down. It stays the same. This is what mathematicians call the identity symmetry, or the trivial symmetry. Together, these make up the 6 symmetries of a triangle. But wait, you might say. We can rotate it 3 times and it will appear unchanged as well. We can rotate it clockwise and it will appear unchanged. But remember, only the end result matters here. The path we take to get there doesn't. If you think about it, rotating it 3 times is the same as doing nothing. Rotating it once, clockwise, is the same as rotating it twice, counterclockwise. What about 2 in a row? Well, to do 2 different transformations in a row, mathematicians call this multiplying transformations, it looks as if you've only done one of the 6 symmetries once. A symmetry followed by a symmetry is also a symmetry. No matter how many transformations enacted upon a triangle, the end result can always be obtained by doing one of the 6 transformations. These questions begin to touch on a type of math called group theory. The set of all symmetries is called a group. By looking at this group, it is possible to understand how the symmetries interact. The easiest way to understand this concept is by making a chart. Okay, so let's assign a letter to each of the 6 symmetries that make up a triangle symmetry group. Let's call the identity symmetry I. Rotating it once counterclockwise, O. Rotating it twice, T. Reflecting it across A. Reflecting it across B. And reflecting it across C. Okay, I, O, T, A, B, C. On the left-hand side of the table, we'll put all of the transformations done first, and on the top, we'll put all of the transformations we can do next. We're going to be multiplying 2 transformations together here. By thinking about what happens to the triangle in each case, we can fill in the table and see how the symmetries interact. Now you can see doing nothing, followed by doing nothing, is obviously equal to nothing. Rotating it once, followed by rotating it twice, is also equal to doing nothing. And reflecting it across C, followed by rotating it once, is as if we just reflected it across A. Just like when we multiply numbers, we could multiply 3 transformations by doing 2 at a time. But let's go back and look at the symmetries of the Alhambra. We aren't dealing with individual shapes anymore. Instead, we're looking at repeating patterns on a plane. Patterns that only repeat in one direction, like this one for example, have one of 7 symmetry groups called frieze groups. but the walls of the Alhambra are even more complex than that. Their patterns repeat in two directions covering the plane, and in this case, the walls. As complex and different as they seem, the patterns can be classified into 17 different groups, so-called wallpaper groups. The patterns are classified into the different groups by their symmetries alone. Patterns that have the same symmetry fall into the same group because the group is defined by the set of symmetries an object has. There are only 17 distinct wallpaper groups for a plane. Essentially, if we were to figure out all the different combinations of symmetries a pattern can have, we would find that there can only ever be 17 groups. Just like with the triangle, we need to think about what types of transformations we can do that may leave the pattern intact. They're called isometries. There are 4 types of isometries. 2 of them are similar to the triangle's types of symmetry. These are translation, which is moving a pattern in one direction along a line, rotation, which is spinning a pattern around that point, much like what we did with the triangle, reflection, which is reflecting a pattern across an axis, and the last is what is called a glide reflection. This is essentially a combination of translation and reflection, and involves translating a pattern along a line and then reflecting it across that same line. Now, depending on what the pattern is, we can perform some of these translations and leave the pattern the same. Which of these motions can be performed dictates what kind of symmetry the pattern has, and therefore which wallpaper group the pattern can be classified into. Keep in mind that 2 patterns don't have to look similar to be in the same group, they just have to have the same set of symmetries. Having this type of design on the wall forces us to focus on the intellectual aspect of our dual nature, our mind over our body. When choosing between representations of the mind of God or the body of God, the Moors chose the eternal over the temporary to adorn their walls. Rather than picture fleeting terrestrial forms, they chose the eternal truth of mathematical pattern to illustrate the mind of the divine. The universe has pattern and symmetry, and the walls of the Alhambra were meant to raise our awareness and appreciation of those patterns.